In this lecture, we'll talk about some of the properties of the determinant. Well, first, let's take a look at a 2x2 matrix A. Let's say A equals to A11, A12, A21, A22. Okay, and then if we applying the first row operations on this matrix A, first row operations. Remember, the first row operations is the operation when you interchange two rows or swapping two rows, right? And in this case, it's only two rows, so I just swapping row 1 and row 2 to get, let's say, A1, which is a new matrix. Using the first row operations, you have A21, A22, A11, and A12. And again, this is a lecture in the determinants, so it makes sense to find the determinants of A. So what is the determinant of A? We know that we use cross multiplications, A11 times A22 minus A12 times A12. Okay, and then what is the determinant of A1? So let's say the determinant of A1, right, is the new matrix after you apply the first row operations onto A. It's going to be equals to A21 times A22 minus A11 times A22. Okay, and you can see that the determinant of A and the determinant of A1 is the opposite of each other. A11, A22 here, A11, A22 in the back, and so on and so forth. So this is, from here, I can conclude that it's going to be equals to the determinant of A1. Okay, so the determinant of A is equals to the negative of the determinant of A1. If A1 is the results matrix from using the first row operation on the matrix A. And you can rewrite it as determinant of -1 times the determinant of A. All right. What about using the second row operations? Say second row operations, which is when you multiply one of the rows by a non-zero constant. So let's say I take row 2 and I multiply row 2 by 2. Okay, so if I do this, then my new row, my new matrix A2, I call this A2 equals to A11, A12, 2A21, and 2A22. Okay, and then from here, I want to find the determinants of A2, which equals to 2A11 times A22 minus 2A21 times A12, and you can factor the 2 out. A11 times A22 minus A21 times A12, and is this here? It's just the determinants of A. So if you multiply a row by a non-zero constant, the determinant of the new matrix is equals to the constant times the determinant of the previous matrix. So 2 equals to 2 determinant of A1. All right. Well, how about the third row operations? Let's say you take row 1 and you add -2 row 2. Okay. Well, then the new matrix A3 will be equals to row 1 would be changed, right? And row 1 minus 2 row 2. So it's going to be A11 minus 2 A21. and then A12 minus 2, A22. And then A21, A22 still stay the same. And then from here, you want to find the determinants of A3. Will be, again, you use cross multiplications. So I would have A22 times A11 minus 2A21. Okay. Minus A21 times A12 minus 2A22. And I will try to simplify it. So this is going to be A11 times A22 minus 2A22 times A21. This is going to be minus A21 times A12 plus 2A21 times A22. Okay. So from here, you can see that A22, A21, A22, A21, this is minus, this is a plus, this is gonna be canceled. The leftover is just A22 times A11 minus A21 times A12, which is the same as the determinant of A, which is equals to just 1 times the determinant of A. So the determinant of A3 would be this. So from these three examples, as you can see that if you apply one row operations on a matrix, then the result matrix will functions in a different ways depending on which row operation that you are using. Okay. For example, for the first row operations, the determinants of the new matrix will be the opposite of the determinants of the previous matrix. You multiply the determinant of A by -1 to get the determinant of A1. Okay. What this should be, so this should be A1 here. Okay. From here, you know that the determinant of A equals to the negative determinant of A1, or the determinant of A1 equals to the negative determinant of A, so just opposite of each other. And then if you use a second row operation, and if you multiply a row by a non-zero constant, then the determinant of the new matrix here equals to the same constant multiplied to the determinant of the previous matrix, or the original matrix. And then if you if you use a third row operations, which you mean when you like multiply, add or subtract multiple of one row to another, then the determinants of the two matrices are the same. Okay, if you use a third row operation, then the result matrix will have the same determinant as the previous matrix. Okay. So that's one properties of the determinant related to row operations. And keep in mind that for one row operation, you will have an elementary matrix that corresponding to each of the row operations. And let's say it here. So for the first row operations, the elementary matrix for this row operations is, let's say E1, right? Equals to, if you interchange row 1 and row 2, it should be 0, 1 and 1, 0 here. Okay. And then you know that A1 equals to E1 times A. Okay. And then we know that the determinant of A1 equals to -1 times the determinant of A, which means the determinants of E1 equals to -1. Okay, this is one thing that we can find from this example. So the determinant of an elementary matrix of the first row operations is always -1. All right, now go to the second row operations. For the second row operation here, as we know that we can find E2, okay? E2 will be 1, 0, and 0, 2, because you multiply row 2 by 2. And then we know that A2 equals to E2 times A. And we also know that the determinant of A2 is 2 times the determinant of A, which means the determinants of E2 probably equals to 2, right? And we know that determinant of E2 is 2 because you can find it. You can find this determinant of E2. So then you know that if E2 is an elementary matrix corresponding to the second row operations, then it is going to be, the determinant will be the same as the non-zero constant that you multiply to one of the rows. How about the third row operation? Did you already guess that the determinant of the third row operation should be 1 at this point, right? Yeah. So you have E3 equals to 1 minus 0 is 1, 0 minus 2 is -2, and 0, 1. Okay, and then you find the determinant of E3, you would get 1 times 1 is 1. Minus plus 2 is 3. So this, hold on, this is, seems like this is not the determinant of E1. E3. So E3 starting with 1, 0, 0, 1. So 1 minus 2, 0 is 1. 0 minus 2 is, oh, it's equal to 1. Yeah. All right, for some reason I said. So the determinant is this E3 is 1. All right. So we learned how to find the determinant of result matrices after some of the row operations, and we can figure out the determinant of each of the elementary matrices corresponding to different row operations. But the next property, so and then this is the summary of what we just did. So if A prime be the obtained from A by exchanging two rows, then the determinant of A prime equals to the negative determinant of A. If A prime is obtained from A by multiplying some row by a scalar C, then the determinant of A prime equal to C times the determinant of A. If A prime be obtained from A by adding a multiply of one row to another, then A prime, the determinant of A prime equals to the determinant of A. So you have the determinant of A prime. The determinant of an identity matrix is 1, as we know. And then the next properties is a lemma. Is saying that if A is a square matrix and big AJK denotes the cofactor of small ajk for k from 1 to n, then if you take little a I1 times big AJ1 plus little a I2 times big AJ2 and so on and so forth, then this sum of the product will be equals to the determinant of A if I and J equals to each other, which makes sense, right? If I and J the same, then this is just the formula of finding the determinant of A. But then if I and J are different, then the sum of the products here will be 0. Okay. So again, big A is a cofactor of little a. So if I and j are the same, for example, A11, big A11, then this is the formula of the determinant. But then if you have little a 1, 1 and big A 2, 1, then these two values here are not the same. Then if that's the case, then this sum of the products will be just 0. And the proof is in the book. The proof is saying that if you replace the matrix A, one of the row of the matrix A, by another row, then you can find the determinant of the new matrix, and then you can figure that this formula works for that new matrix. Okay, keep in mind, if you have this sum of the products, I and j here, where big I is the cofactor of little I, ij, then the determinant is going to be the determinant of A if I equals to j. Otherwise, it will be just 0. Well, then the next theorem about determinants is, if A be an arbitrary square matrix, then the determinant of E times A is the same as the determinant of E times the determinant of A. I mean, we have seen this, right? We have seen this fact up here. So the determinant of E1 times A is the same as the determinant of E times the determinant of A, when E is an elementary matrix of any of the row operations. Okay. And then the next theorem is, if A be a square matrix, then A is singular if and only if the determinant of A equals to 0. So in this theorem, we learn how to figure whether a matrix, a square matrix, is singular or non-singular when we can determine the determinant of A. So let's try to prove this. So if if we have a matrix A, right? A be an n by n matrix. And let U be the reduced row echelon of A. Okay, so you reduce this matrix to U. So that implies that there exists a series of elementary matrices that would take from A to U. U equals to EK, E2, E1 times A, where EI are elementary matrices. Okay. Well, at this point, we know that the determinant of U equals to the determinant of EK, E2, E1, right, and A. So you can see that the determinants, and then you can keep, because of this properties right here, you can actually separate this product into single determinants. Okay, so then you can analyze it this way. So if A is singular, then the reduced row echelon of A should have at least 1 0 row. Then U has at least 1 0 row. 0 rows mean the row that contains all 0, which implies the determinants of U equal to 0. If the determinant of U equal to 0, then the determinant of A should be 0 because the determinants of all the elementary matrices are not 0. Thus, the determinant of A is 0. Okay. And in this case, you can think that if A is non-singular, then the determinant of U should be not 0. And thus, the determinant of A is not 0. So in this case, you can show if a matrix is non-singular, if and only if the determinant of that matrix is non-zero. All right. And then go to the next theorem. You have the determinant of A times B equals to the determinant of A times to the determinant of B. So again, we want to show this. You have, let's show, in the case that B is singular. So if B is singular, then A times B is also singular. That means the determinant of A times B equals to 0, right? If A is singular, then the determinants of, if B is singular, then the determinant and the determinants of B is also 0. So that means the determinant of A equals to determinant of A times determinant of B equals to 0. But in the case, it's easier when B is singular. What B is non-singular? If B is non-singular, then B can be rewritten as the form of elementary matrices, right? Because you can reduce B to the elementary, to the identity matrix. So B equals to case 2, right? Where EI are elementary matrices. Okay. And now you can put the determinant of A times B is the same as the determinant of A times this elementary matrices. Because of these properties up here, you can, expand this product out into single determinants. Okay, and then from here, you can actually, and then you keep this determinant of A, but you can combine all of these determinants of elementary matrices into just one determinant. And this is just B. So we just show that the determinant of the products of the two matrices is the same as the determinant of each of the matrix, the product of each of the matrix. In the two cases, when B is singular and when B is non-singular. And from this theorem, we can talk about this corollary. Say if A is non-singular, then the determinants of A inverse equals to 1 over the determinant of A. Do you know why? So we know that I equals to A inverse times A, right? And we learned that if the determinant of A, so that means the determinant of I equals to the determinant of A inverse times A. And we can break this products into the products of two determinants, A inverse times the determinant of A. And then from here, determinant of I is 1. So that means the determinant of A inverse equals to 1 over the determinant of A. This is how you want to show this corollary. All right, keep in mind, in the determinants were the determinants of A times B equals to determinant of A times determinant of B. If A is singular, then the determinant of A should be 0. If E is an elementary matrix, then you can break it down into these two determinants. And if you have a sum of these products in this form, then you have a determinant of A when I and J are the same, and you will have 0 if I and J are different. And then if you interchange, applying row operations into square matrix, then the result matrix will following these rules right here. First operations, you're gonna have an opposite determinant. Second operation, you're just gonna have the same constant multiplied by the previous determinant. If you apply the third row operations, which is nice because you reserve the same determinant, the third row operations. So these are some properties of the determinant. Well, let's look at this example here. Find all the possible choices of C that would make the following matrix singular. Okay, we know that a square matrix is singular then when maybe the determinant of that matrix A is 0. Okay, so I call this is matrix A. And I want to determine C so that A is singular. A good way to do is trying to find the determinant of A. So in order to find the determinant of A, I need to pick a row or a column to find cofactors, right? So let's just say I pick the first row. So it's gonna be 1. And then you multiply by the determinant of cofactor 9C, C3, okay. And then plus -1 times 1 and multiply by 1C, 1, 3. And then plus 1. And then you have 1, 9, 1C. Okay. Well, the determinant of this 2 by 2 matrix is going to be 27 minus C squared minus 1, 3 minus C plus C minus 9. Okay, it's going to be equals to negative C squared plus C plus 2C, 27 minus 3 minus 9, will give you 15. So the determinants of A is 15. Now the goal is you need to make A to be singular. Then the determinant of A has to be equal to 0 for A to be singular. Determinant of A has to be equal to 0. That means, well, negative c squared plus 2c plus 15 equal to 0. That means, it's negative 2, so it should be c equals to negative 3 and negative 5 and 3. So it should pass to 5 and negative 3. Okay. The next exercise. For you, A be a n by n matrix and alpha is a statistic scalar. You want to show that the determinant of alpha times A equals to alpha raised to the n times the determinant of A. So let's say if A is this matrix. So I rewrite A as a matrix using rows of A, right? So A is row 1 of A is A1, A2 to AN, where AI are rows, like row columns, like row vectors of A. A1 is the first row, A2 the second row, and AN is the nth row. Okay. Well, if you multiply alpha to A, then alpha A will be alpha A1, alpha A2, alpha AN. Okay, that's right. You have to multiply alpha to every single entries of A. So as we know that if we we multiply one alpha to one row. That means when you use the second row operations, consider just the matrix A when A equals to alpha times the first row. And you keep the second row and the last of the rows of A. You just multiply alpha by the first row. Then the determinants of A1 should be alpha times the determinant of A, right? Just multiply alpha to the first row. Imagine that in alpha times A, you have multiply alpha by all the rows. That means if you multiply alpha here, then again, you get A2, right? For the determinant of A2 equals to alpha times the determinant of A. So then if you keep multiplying alpha to every single row, then the determinant of AN or alpha A, when you finish multiplying all the alpha by all the rows, then you get the determinant of alpha A, which is, so then you will keep multiplying alpha n times. That means you have alpha to the n of the determinant of A. So here we go. Keep in mind, if you multiply alpha to a matrix, find the determinant of that, it has to be equals to alpha raised to the n because you have to multiply alpha n times, and then you multiply by the determinant of A. Here's some examples about how we can use properties of determinants to solve some of the problems that involve the determinants of a matrix.